Want to hear a noble gas joke? Never mind, it won't get a reaction. Welcome to this video on gas mixtures and movement. We're going to talk today about how gases are when they are mixed together and some things that we can know about those and how they can move from one place to another. So grab your notebooks and something to write with and let's get started. So we first want to talk a little bit about just gas mixtures and what a gas mixture is. So we have this law, so we have lots of laws for gases. So Dalton's law of partial pressure, and when we do this, we are assuming that it's at constant volume and temperature. And if that's the case, what we know is that we have an amount of pressure for the entire mixture of gas, and it's equivalent to the sum of all partial pressures of each individual gas. So basically, the amount of pressure that that individual gas would have in that chamber added up with all the other gases would give us the total amount of pressure. And so we can write this as an equation, sort of. P total is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, and so on and so forth for as many gases as we have in that mixture. And I really like the visual of something like this when we're talking about these. And so in this picture, you can see here that we have our oxygen, okay? So we have our oxygen here, and it's in a chamber. So if we looked at the oxygen, the amount of oxygen in this mixture that we see over here. So here's our mixture, okay? If we look at the individual ones, we can find out that it has a certain pressure. And so this one happens to be in millimeters of mercury, okay? And then we have nitrogen also, and this is going to be the partial pressure. So these are the partial pressures. So this would be like P1, and this would be P2. And then this one is going to be our P total, is the combined effect of both of these, okay? And so if we take P1 plus P2, we would end up equaling the total pressure of both of those gases when they're mixed together in that chamber at constant volume and temperature. So let's take a look at just an example problem that you might see when you are doing some practice problems in chemistry. Okay, so here's one. It says, what is the pressure of O2 in a gas mixture with a total pressure of 30 atmospheres containing 9.6 atmospheres of carbon dioxide and 14.4 atmospheres of N2, nitrogen gas? And so all we have to do is add in what we know. So we know that we have P total is going to be the sum of these three gases. So it's going to be the pressure of the O2 plus the pressure of the CO2 plus the pressure of the N2. Okay. And so I can plug in my values that I know. I know that my total pressure is going to be 30 atmospheres. I know that P of oxygen is what we're looking for, and I have 9.6 atmospheres for carbon dioxide and 14.4 atmospheres for N2, for nitrogen gas. And so then we just want to rearrange this. So now that we're adding, we're going to actually subtract these from both sides. So to find my pressure for O2, my partial pressure for that, I'm going to take 30 atmospheres, okay, and I'm going to subtract the 9.6 atmospheres, and I'm going to also subtract the 14.4 atmospheres. Okay, so subtract those from both sides, they'll cancel on one. And so if I do that, let me plug that into my calculator really quickly. 9.6 minus 14.4, and we end up finding out that we have a pressure of oxygen, okay, P of O2, our partial pressure for this, is going to be 6.0 atmospheres. And so you could be asked for the total pressure, you could be asked for a partial pressure, just any direction that you could possibly work that problem. All right, so that's really all that we need to know about partial pressure. Now we also want to know about gas mixtures, and if you remember from a while back in one of our previous videos, we talked about diffusion and effusion. And so we said diffusion is where gases are going to move from high concentration to low concentration, and they spread out evenly in their space. And so here we see this gas that was concentrated here has spread out throughout the entire gas. Okay, and we also saw that Effusion is where gas molecules are going to escape from whatever they're held in through small openings. And so we use the example of a balloon. And so if a gas molecule should hit this little hole here, it's going to effuse or move out of that container. So with effusion and diffusion, we find out that these happen at a particular rate. And so we want to know about how to be able to judge what those rates are. And so we have a couple things that help us out with that. The first thing that I want you to just really know is that the gases with a smaller molar mass are going to either effuse or diffuse faster than gases with larger molar mass. And so we're going to come back to molar mass when it comes to these. If they're going to be a larger molar mass, there's more going on there, probably going to be a larger gas molecule, it's going to move a little bit slower in its ability to effuse or diffuse. So that's kind of the big idea. And we have somebody who came up with an understanding of this. It's called Graham's law of effusion, and there's a definition for it. I like the equation a little bit more for that. And so what I'm going to do is show you here what that equation looks like. I don't have it digitally made. So basically what we do is we take two gases, and so we're going to say the rate of one gas. So we're going to say the rate for, say, gas A compared to the rate of gas B, so this is the rate at which they would effuse or diffuse, either way, is equal to the inverse square root of these things, and so of the molar masses. And so we're going to put the molar mass of B on the top divided by the molar mass of A on the bottom. So whatever was up here will move down, whatever was down here will move up with their molar masses, and you want to take the square root of the entire thing to find out that value. So when we go to do this, we'll take a look at an example here in just a moment where we'll see this. We really do see what that general rate is going to be. Okay, so we're using those to establish that rate. And so here we see that since neon is going to be bigger, it's going to take it a little bit longer to either effuse or diffuse, whatever it might be doing, in comparison with something like helium that would be smaller. So let's take a look at an example problem with this. This says, what is the ratio for effusion of helium compared to nitrogen gas? And so we're going to start with these, just like we did in our equation. We're going to say that the rate of helium, okay, so rate of helium compared to the rate of nitrogen is going to be equal to the molar mass of helium. Okay, so on the top we're going to put the mass of helium, which is 4.0 grams of not helium on the top. Let's do that over again. So the rate of helium has to go on the bottom on the other side to the rate of nitrogen. Okay, so we're going to put the 4 grams for helium here, and we're going to put the 28 grams. Remember, nitrogen's 14, but there's 2 of them, so it's 28 grams for nitrogen on the top. Okay, and we want to take the square root of that. So the first thing that we want to do is we want to divide. Okay, so 28 divided by 4 is going to give us 7. But we want to take the square root of 7, and we're going to find out that our ratio is going to be 2.7. Okay, and that tells us that helium actually is going to be to effuse or diffuse 2.7 times faster than nitrogen. And that's really all we need to know about those. So I hope that was helpful for you. We'll take a look at some practice problems when we get back to class.